Hi everyone. I had the wrong stream title up, so I don't know if students were coming and looking at that and going, oh, that's the wrong class, and leaving. So I'm going to let it run for a few more minutes before we start. Enjoy the wonderful 80s theme of Paradise Killer, which, yeah, Ghostbusters, same era, right? Alright, we'll start in a few minutes. Alright, that's a little better. Looks like we have more people now. So we'll fade this music out here. And we will get started. Welcome back to Chem 140. Today on our agenda, we are doing Unit 2. We're probably going to finish it. I don't think we need to go that much faster than that, but we're going to do some basic algebra. We're going to talk about how to do math using this new concept that we're talking about here called significant figures. We learned yesterday that when we measure stuff, there's going to be some error associated with our measurement because tools aren't perfect. And that if I use a ruler and I measure between two marks, I only get so many digits based on what those marks represent. We're going to take all of that together and put it into a representation of that information in the form of just a number. Okay, and we're going to need to worry about how we represent those numbers from this point forth. Now, the important thing that I want to comment on before we even start this discussion is this is not just a curiosity. This is not going to be something where it's like, oh, that's interesting. Okay, yeah, that's how we do this. And then we never deal with it again. Significant figures is going to be a method of doing algebra and mathematics that you will continue to use forever. You will not be doing math the old way, we'll call it, ever again, and just punching a number in your calculator and keeping as many digits as you want. There is a specific way to represent what information is well known and separate it from what is just essentially random numbers that don't have any meaning based on the measurements that we got. I'm going to open this discussion with a little story of somebody who wanted a manufacturer to make a cube for them. So I'm going to just draw a cube real quick. And so the guy, person A, was like, yeah, I ordered this 3-inch wooden cube, and they did a really good job on it. And they're like, and so person B was like, wow, that's really cool. So person A said, okay, I have a 3-inch cube. Person B went to the engineers or the manufacturers and was like, hey, I want a 3-inch cube, and told them this number. And they're like, okay, that's going to take a long, long time, and we're going to have to do it multiple times to make sure that we get it right. And the person B was confused, like, why? Sure, whatever. Okay, it doesn't make any sense. But then person B gets the bill back and is like, holy crap, why is this so expensive? My friend told me it didn't cost anything at all. And the answer to this question was, well, you told us that you needed to have this much precision. If you needed it to be 3.000 inches, that means we can't be very far off in that last digit at all. But if you're doing something like this, then we can be relatively close, and you can do it very easily. I could just do this in 20 seconds. This is going to take like a day. We're going to have to measure it out, make sure that we have the right tools, etc. So these two numbers are not the same at all. And if I were to do math with them, we're going to need to take into the consideration that they're not the same at all. Adding something like this to 3 is going to be very different than adding it to this, because these numbers are known, but these numbers aren't. What does that mean for us? That's the topic of today's discussion, okay? All right, so let's get started. Whenever you make a measurement with some sort of tool, the number of digits that you can write down as either known or closely estimated, which is the last digit. The number of digits you can write down is the number of significant figures you have in your result. The more digits that you write down, the more well-known your result is. So in this number right here, 11.64, I wrote down 1, 2, 3, 4 digits. So that value has 4 significant figures. If I were to write a number with more digits in it, like this has 1, 2, 3, 4, 5, 6, 7, 8, 9 digits in it. That's 9 significant figures. And as you can tell, when two numbers have the same magnitude, this number up here was probably measured with a ruler. This number down here is very, very precise, and this was probably measured with like an electron microscope to determine that distance. One of those you can buy at the dollar store for like 20 cents. The other costs like $20 million to use, and it gets you more digits that are known. Okay? So we represent how well known a number is by the number of digits that we can write down. Note that I am saying digits and not decimal places. For example, if I say that there are about 4 million people in the state of Washington, that is a much cruder estimate than if I said that there are about this many people in Washington. You'll notice that I wrote down more digits here. Instead of just putting in placeholders, I wrote digits in there. And so that's going to be an interesting thing to note here. What do these zeros even mean? Like, are those actually digits? I wrote a 0 there. Isn't that a digit? Yes and no. And we're going to talk about that later too. Okay. The more numbers you write, the better known the number is. Now, when we're going to do calculations with these numbers that come from measurements, we're going to need to worry about how many significant figures are in our numbers so that we can use them appropriately. Okay? Like we said on the previous page, any digit that isn't 0 is a significant figure. When we have 0, it depends on how it's used. So we're going to look for non-zeros and count them as sig figs. And if all your numbers are not zero, you're set. If you have a zero, it depends on how it's used. And we're going to look at some various situations where zero is applied as a sig fig and other situations where it's not. The first situation we want to talk about is the placeholder. Here's how we work with placeholders. I'm going to give you an example here. Let's suppose that I owe you this much money. That's a lot of money, right? Let's suppose that I owe you $3,996. You know what I'm going to do? I'm going to make it easier on all of us. I'm going to just round it to $4,000. And then what I'm going to do is I'm going to say, well, those zeros have no value. So I'm going to erase them. And I'm going to pay you this much. Are we square? Is this okay? Would you accept this deal? Yeah, I'm just going to pay you $4. We'll round 3,996 to 4. Hopefully your answer isn't just no, but fuck no, right? Like, that's not how numbers work, right? That's ridiculous. So, this is not how rounding works. What this means is that those zeros have a purpose. These zeros are called placeholders. Placeholders have no value and don't impact the result of the answer other than to change the magnitude of the leading numbers. So this 4 right here is the leading number. If I were just to put the 4 here, then this is just 4. 1, 2, 3, 4, right? If I only have 1 0 there, then this is 40, but not 4,000, right? I want 4,000, not 4 tens, right? So I need to put enough zeros to force this number into the correct place. Each zero I add moves it over into the correct place. To represent the magnitude I want, I need enough zeros to push it into the thousands place, because the number I started with is in the thousands place. Okay? Zeros used in this way, with the purpose of changing the magnitude of our leading number, are not significant figures. They are there only because they have to be. I cannot write this number and represent it as a 4,000 without doing something else to it. And there are two options. One of them is to do this that I did above. The other is to do this. Scientific notation. We'll talk about scientific notation in a little bit. But by doing either of these, if we don't count these zeros as sig figs, and we only count the leading digits, we now have the correct number of sig figs based on our rounding. All right. So as you can see, my 4,000 is a crude measurement, but 3,996 is much more reasonable. We're going to talk about different situations and different numbers of sig figs and also precision and accuracy as we go on. But anytime you see 0 and it's used specifically as a placeholder, it's not intended to be significant. Now, if you aren't sure if something is a placeholder or not, there's an easy test. And that test is, to delete the zeros and see if the value of the number that you wrote down changes. Is 1,250,000 the same as this number shown here, 125? If the numbers are not the same, then what you erased were placeholders. Okay. Same thing with decimals. If I go in this direction, and I erase these numbers here, so these are gone, that number, 4,386, is way larger than the intended number. I am putting these zeros in front of it to make it so that that 4 shows up in the place that's intended, which would be the 100,000ths place. All right. if you have zeros that fall between other significant figures, those zeros count as significant. So over here, if I go like this, these zeros change the value by pushing it into the correct magnitude. Now, we cannot apply the same standard to this zero, and the reason for that is the following. If I had a scale that measured like this, and so this is my last known digit, and this would be my estimated digit. Because remember, when I measure, all of my digits are known except for the last one, which is closely estimated. So if I had marks on a ruler that look like this, since my known digits are where the marks fall, it would look like this. 8, 6, 7, 5, 3, 0, 8. Oops, I'm sorry, that's not right. Also, I ran out of space there, too. Oh. Oh, 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 oh. One, two, three, four, five, six. Like that. So this is what our marks would look like on this ruler, because again, we're going to the last known spot. And then if I measured something on this in my scale and it was like, whoop, like that, what I would do using the measurement rules is I would write down the two marks and write down the value of the lower mark. Yeah, this is Jenny's number. Yep, so you recognize the joke. Good. And then I would guess the next digit. So, oops, sorry. I didn't mean to draw through that. There we go. So I know this is 0, so I'm going to write that 0 down. And then now I have to guess the next digit, and I had to guess the next digit to be 0. And there's Jenny's phone number. All the rest of these would just be placeholders. That's how I get you to remember these examples. So these are my placeholders, but this number is known. Just because it's 0 doesn't mean that we can't still know for sure it's a 0. Whereas in these other numbers over here, these could be any numbers that we wanted to. We have rounded them to 0. For example, if this was like 43275, that would still round down to that if we rounded to this position. So any numbers that we don't know at all will get rounded down to our placeholders. All right. I gotta clear all this here. The last important rule for identifying if 0 is significant is called the decimal rule. And so if you have a decimal, any numbers to the right of Sig Figs are also Sig Figs. So this is really easy to apply. Let's write down a number here. All right. So step 1 in the decimal rule, find the decimal. There it is. So if you see a decimal, you must apply the decimal rule. Must. Okay, this is not optional. Once you have found the decimal point, any zeros to the right of Sig Figs are also Sig Figs. So first find the Sig Figs. That's these. They're non-zero. And then any zeros to the right are also significant. Any zeros to the left are not. In other words, what that means is if I were to write this number, there's a reason I wrote that instead of this. And that reason is that I know this digit and I reliably estimated that next digit. So in other words, if I was looking at let me trim this down a little bit. If I was looking at a scale for this value, I scrolled it the wrong way. What am I doing? So that scale might look like that didn't do anything. Oh, there we go. It's just really slow. And so I would have marks on here. I have a cat meowing at me now. Maya, please. Maya. I don't know if you can hear her, but I don't know if you've met Maya yet. Hold on. Maya, come here. Maya, what do you have to say to the class? Hi. Hi. Say hi. There we go. Maya says hi. She also wants me to hold her because that's all I do is hold her. All right. Let's suppose that I had a scale like this, and so you can see that this goes to 1, 2, 3, 4, 5, 6 decimal places for each of these. I counted this 0. Oh, she's so sad, you guys. She just... Maya, I'm teaching. Maya. Maya, no, you cannot jump on my lap right now. Okay, now she's leaving. Let's suppose that on this scale, my number landed right here. Right on the line. So what I would do is I would then write this number, because it would fall between these two marks. So I'm going to write the lower number. And then I'm going to guess the next number, which I would guess to be 0. So these are circumstances where you might have to include extra zeros. You just happen to land right on a line when you measure. You need to include that 0. It doesn't just disappear. This is a problem when you're using like a computer or something like Excel or your calculator or etc. Your calculator thinks zeros are extraneous, and so all this time you've been trained to sort of just ignore them. Oh, if the answer was 0.20000 and you hit enter, your calculator says those zeros aren't necessary. I'll write 0.2, and that's not okay in science. So we're going to concern ourselves with how these zeros are written. So be very careful and make sure you are minding these rules. Look to see what zeros are placeholders, and look to see what zeros are written because they are necessary in a decimal. Okay? Once you know these rules, then the next objective is to count the number of significant figures in a value. So let me erase the text on here. So if I were to apply the decimal rule to this right here, these 3 are significant figures because they're not zeros. These 2 are to the right of those sig figs because I have a decimal. They count. Everything else is a placeholder. Now, when you have a decimal place, you cannot do the cover-up thing, so I can't go like this and go, oh, the value changed. Because the decimal implies that all of the numbers that are written there to the right of sig figs are necessary, whether or not the magnitude changes. You're going to see an example of that in a practice problem right here, actually. Okay? So if you are given a number like this and you have a decimal point, the decimal rule is important. Here are my sig figs. All of the zeros to the right are also significant. And so I would have to count them as significant figures. Even though going like this would scribble them out and change their value, because the decimal point is present there, it is implied that they are known. Okay? You only write a decimal point if you need to in order to affirm that the numbers are known. Okay? So be very careful about writing numbers. Don't just put dots in there randomly. The decimal point is a very crucial tool in discerning what the number is intending to be. That's probably not something you've ever thought about. You've probably just thought of the dot as like, oh, this separates whole numbers from fractional numbers, but it actually means a lot more. So we're going to slowly just start doing some practice and getting into the habit of understanding what that decimal point means, okay? All right. Some textbooks are really bad about this. I forget if the OER is good or bad. I know some textbooks like to do this thing where every number is implied to have 3 sig figs. I don't remember what our online text tries to do. If you aren't sure of a number and how it's written, take a picture of it and send it to me, and I will be able to tell you from the context. Most of the time, you should just be interpreting things based on these rules. All right. This comment down here is from the old textbook. So this is old. I realized the letter O went off the screen there. I have more space to work with than you can see here. So this is old and may not apply to our online textbook. All right. Here are more examples. Again, significant figures are non-zero, so let's just start by underlining those. If there's no decimal point, these zeros are just placeholders. These zeros here are placeholders. These zeros are significant because there is a decimal point. These zeros are significant because they're sandwiched. They fall between known values and just happen to be 0 on our scale. And then there's a decimal point right here, so this 0 is significant because it's to the right of a significant figure. All right. One last issue that we're going to come up to is there a way to write this number shown down here to have 3 sig figs? And there is, but we'll talk about it later. It involves scientific notation. So for now, we're just going to be counting sig figs. So let's do that. Oh. We're going to do that with our measurements here. Okay, so we'll do that in a second. Why do we care about significant figures with measurements? The reason that we care is because significant figures are a tool that allows us to show how precise something is. A number with 2 significant figures is not as precise as a number with a lot of significant figures. So if this is 2 sig figs, and this is 1, 2, 3, 4, 7 sig figs, we could draw these conclusions. The tool we're using is very precise. There is little error between our measurements. Okay? So the more digits you can write down, the more precision you have, and the more confidence that you can have with your answer. Now, if we have an exact number would imply this. Exactly 2 would be 2.0000000. All those zeros are known forever. There are an infinite number of sig figs. Oops, I got to get the... I changed the highlighter color there. There are an infinite number of sig figs for exact numbers. And the reason for that is because I know all of these are 0. It's exactly 2. It's not 2.000000001. It's exactly 2. Everything else is 0, and I know that forever. So an exact number has an infinite number of sig figs. Any other number that's measured will be inexact and will not have an infinite number of sig figs. Now, when you have a tool, and you use that tool to make a measurement, you will get a number that gives you a certain number of sig figs. But what if we want to go backwards? What if I give you a number and I want you to look at that number and imply information about the tool that you're using? Well, let's do an example of that and show how this thought process should work. So, for example, which of these graduated cylinders, and the answer could be all of them or some of them or none of them, or just one, which graduated cylinder, if you were to record the measurement from it, you could record a number of 540. And so what I want you to do is I want you to look at each of these graduated cylinders and apply the measurement rules. Use the 2 marks and what place they're in to get a measurement. Now, I don't know why there's this bottom mark here, but the bottom of each graduated cylinder is 0. This part is just zoomed in. So for graduated A, B, and C, let me know what number you think you should report for A, for B, and for C. Try not to look at the slides with the answer on them. And then we'll talk about why you get these numbers, okay? So I'll give you 2 minutes to do that. We'll go over the answers together in just a second. All right, we got a variety of answers, and that's good. We've all eliminated A, and I can tell you that that is actually correct. Why is that correct, though? So let's look at what we would measure here. I'm actually going to erase the 0, and I'm going to write this here. 0, 0, 0, 0. Because these marks are every certain amount, right? They are every 1,000. So what I would conclude is that between the marks of 0 and 1,000 here, I would conclude that I have 0,000 so far, and I could guess the next digit, which is the 100th digit, to be about 5. But after that, that's all I get. The remaining zeros get rounded away to become placeholders. So this volume would be about 500 milliliters, and that's the best that I could tell. All right, let's look at graduated cylinder B. Let's look between my marks. My marks are now in the hundreds place, which means that I know that my value falls between 500 and 600. So I'm going to write down 500. Then guess the next digit. Well, I'm going to guess 4 since we're trying to get 540 anyway. Any digits after that, which are placeholders, are 0. Finally, over here, I know that my answer falls between 540 and 550, so I'm going to write 540 down, and then I'm going to guess the next number, which would be like 544 or something like that. I don't need to write any other zeros because that would change my magnitude if I did this. And I don't want to write a decimal point because that would imply that I know those numbers. So of the graduated cylinders that should tell me which one says I have a volume equal to 540, the only one that does is graduated cylinder B. So hopefully you can see that by looking at this, the more marks you have and the more precise the marks are, the more digits you get to write down. The more digits you write down, the more precise you know the value of the liquid. Or the value of whatever it is you're measuring, okay? So the marks matter, and the number of digits you write down matters too, okay? If I write down that I got 540 milliliters, that means that I had to have used graduated cylinder B to do that, okay? And that I didn't know what the tenths or the ones place is. I don't know what number this is. I could have actually gotten 536, but on this scale, that rounds to 540, and that's all I can tell. I could also have gotten 544. It all rounds to 540, right? Your lab is also going to do a discussion that is very similar to this, which is, here is a bunch of glassware. Oh, wait, I'm sorry. No, that's 161. I'm mixing up my labs. You're not going to worry about that for this lab. But you guys do that on the next lab. Lab number 2. Lab number 1 is much more straightforward. You watch me run around a lab and mix things for lab number 1. All right, so I'm going to give you 4 problems to try, and what I want you to do is tell me the number of significant figures. And so for this first video, what I'm going to do, I don't want to add it to favorites. Actually, what I'll do is I'll do it this way. I'm gonna give you the link for this video because if I play it, I'll get a copyright strike. But when I did this slide, I copied this video and I counted the number of hits that it had. And so I'm going to paste this in here. And so tell me the number of significant figures that that number has, and then you can watch the video and see if you're right. And then finally, do the other 4 things. Tell me how many sig figs each of those numbers has. I'm just checking to make sure the video goes to the right spot. Yeah, it does. Oh, have I betrayed the trust of my students? This is why you shouldn't click on mysterious things that people put in chat. Just remember this when evaluations come around. I don't think you're evaluating me this quarter anyway. It's fine. 3 out of 5. Rick rolled us on the 3rd day of class. Would not take again. I can't believe... So I wrote that slide last quarter. And between now and then, I think it has added 100 million views. Which is just insane. Yeah, it's already 100 million views farther. Maybe that's been in the last year and not the last quarter. That's got to be the last year. All right. But yeah, you can see why I'd get copyright struck for that, probably. Or maybe not, like, because everybody gets rickrolled, right? there we go. All right, so let's go over the answers here. I don't want that to show up just yet because we're going to talk about that in a second. All right. How many digits are written in this first... I had the arrow selected. I want the pen selected. There we go. So I got 3, 6, 9 digits. I have some zeros that are trapped in here, but they count because they're between sig figs. So I have 9 significant figures. Now, believe it or not, this is one of the first questions I ever wrote as a teacher, which I started in like 2008. I was fresh out of grad school, and I was like, what numbers would make good for significant figures? And for some reason, I thought of 90210, which was a TV show that had aired when I was a child. And then last year, they brought it back, and it was still terrible, and then they canceled it, I guess. So this, I might have summoned it, I guess. I don't know. Anyway, these digits are significant because these are not zero. This is a sandwich zero. There's no decimal point, so this one is not significant. Down here, I do have a decimal point, so I do have to pay attention to the decimal rule. So these count, and this counts because it's to the right. And then finally here, I have a decimal point, which means that I have to follow the decimal rule. All of them count. Remember that 500 dot has 3 sig figs, but 500 only has 1. All right, so be mindful of that. Now, this message that I kept accidentally flickering on the screen here, let's put it up here. Let's talk about this just a little bit. I'm going to clear the screen here so I have space to write. So let's suppose that I was using some sort of device to measure these. What uncertainty would I put after each number? As in, where is the uncertainty in my measurement? And so that depends on my sig figs. Now, the first one is kind of unfair because this is just counted, so this is exact, so we don't really have to worry about it. But if I was considering it as a measured number, I would do plus or minus whatever position was the last sig fig, and so that would be plus or minus 1. Over here, the last sig fig is in the 10th place, so I'd do plus or minus 10, because that's what that measurement tells us. And then over here, this last sig fig is in the, what is this? 10,000, so it'd be plus or minus 0.0001. Something like that. And then this is the ones place. Like that. We're not going to worry about uncertainty in this class. In terms of, there's a physics uncertainty where you can calculate it using standard deviations and statistics. We're not really going to worry about that. This is a very basic understanding of uncertainty here. We're not going to worry about that because we don't do any statistics. We don't have enough sample sizes to really care about it. The first number is exact because it's counted. And so so what I'm doing here is we're assuming that each of these is measured with some device. And that's why we're counting sig figs. For this exercise, I am just making you count digits. And also, I wanted to rickroll you, so I had to make up the problem. So if you had written on this, oh, this is infinite number of sig figs because that's a counted number, I would accept that as correct. But for the purposes of the exercise, like how many sig figs are in this value, it's just 9. But you're right, you have the right idea that, wait a second, that's counted. It absolutely is counted. It's counted by YouTube. So good thinking. You're thinking beyond the scope of the problem. All right. Now that we know how to count sig figs and numbers, what we're going to do, and we're going to take a break a little bit early because we're probably going to finish slightly early because this is the last section that we're going to cover today. We're going to talk about how to do math with these, and that's going to take some practice. So we're going to get our break in now. That's not the screen I want. I want this one. Let's get the timer back up here. We'll go back to Paradise Killer for some more crazy 80s music. All of my students from the first period were like 18 and 20. So they weren't around when this type of music was actually played, but this is music from a great game and I really enjoy it. So, we'll start the timer, we'll start the music, and we'll see you in just a little bit. Oh, close enough. I mean, the music lined up pretty well there, so I'm happy with that. All right, what do we got going on now? Welcome back. It's time to do math. Time to break all of our brains. What we're going to do in this section is not hard. The rules are very simple, but it is in the simplicity that novice students get lost. And what I mean by that is I'm going to teach you two rules. And one of the rules is easier than the other. And what people tend to do is they apply that rule to everything. Be careful, okay? Knowing the mistake that is likely to happen at the start could help out. And so that's the advice that I give at the onset of this. Be careful about these two distinct rules that we're going to talk about, okay? I'm going to start that conversation with two problems that are very basic. Anyone in this class can solve these problems. Can you do addition? Of course you can. Can you find area? Sure. Those are very easy things to do. However, it turns out that all along we have taught you 95% or so of the correct way to do them. In science, we need to consider the consequences of measurement in significant figures. And we're going to do that in the following way. We're going to start with example A. I'm going to do addition. If I were to add these numbers together, I would treat these blanks as nothing, and I would just carry the numbers straight down, right? 8, 14, 18. I've already messed up. Where's my eraser? There it is. Oh, I don't have an eraser on this mode. I have to do it that way. So 8 and 4 is 12. 14, 18, 19. Doot. 11, 12, 15. Doot. That's supposed to be a 5. Whatever. Doot. Okay. So I get 535.921 should be the answer if I were to just put this in the calculator and hit enter. But in reality, we have an issue, and that issue is when I make a measurement and I round that measurement to 352.8 in the tenths place, what is the number that goes here? Is it 0? Because remember, if I measure this, 352.84, it's still 352.8. If I measure 352.79, it's still 352.8. I could have any number in this spot. I don't know what that number is because the other number next to it is the last significant figure I wrote down, and it's estimated. That 8 could actually be a 7 if the next number is 9. That 8 could be an 8 if the next number is 0 through 4. There are a few possibilities, but because this last digit is our estimated number, there's some uncertainty with it, which throws this number into complete chaos. I have no idea what this number could be. And likewise, if I don't know what this number is, I don't know what this one would be, or this one, or this one, or after that at all. So in reality, these are not zeros that I am adding together. They are question marks. And when I do addition, can I add 1 plus question mark and know that it's 1? And the answer you should be saying is, oh, no, it could be any number. This 1 could be any number as well. Same thing up here. 8 plus 4 plus question mark is not 2. It's question mark. But when I get over here, these numbers are known. And there will be some influence from other numbers that are also known. So what I'm going to do is I'm going to do the math assuming that everything is zeros, but then any positions that have question marks in them, I'm going to just chop them out. I'm not going to use this information. Now, the systematic way to do this is to say, okay, I'm going to start from the right, and I'm going to look at each position. Is there a number in this column that has a question mark that I don't know? If there is, I can't use it. How about this column? There's a question mark. I can't use it. How about this one? Hey, these are all numbers. These are all known. That's where I keep my answer to. Okay? So when you do addition, we are going to concern ourselves about which place we get to keep our numbers to. And that place will be, starting from the right, the first column that has all sig figs in it. Okay? Blank question marks are not sig figs. They are not numbers. They are unknown. I can't do addition with unknowns. So on the next slide, it goes through that again. Here are my question marks. These are question marks because I have question marks in those columns. But this is the first position in which I have a sig fig in all spaces. You're going to start all the way from the right and work your way to the left. And the first one you hit is where you keep your numbers. When you do your rounding, I typically just do traditional rounding. I don't do banker's rounding because we are not doing statistics with a large number of samples. Statistically, banker's rounding is more precise. It does what is called round towards zero, which means that your deviation of error does not slowly creep up and give you a higher and higher number. However, when you only have one sample, which is the number you're working with here, that tends to add more error than it removes. Should we always be adding numbers prior to admitting unknowns? Yes. So do the addition first, and then round for sig figs. Because notice that this 8 and this 4 here made this a 9. So we know that with confidence that 9 it could possibly be 9 or 8, the previous number, as opposed to 8 or 7. It can't be 7 anymore because I have numbers that are just too big here. And that's, again, that is a sort of a philosophical, oh, this last number is our estimated digit. So what would I estimate it to? Well, it could be 9 or it could be the previous number 8, depending on what these numbers over here are. So yeah, do all of your calculation with all the digits and then truncate to the correct number of sig figs after you've done the math. Now keep in mind, we are only discussing addition here. When we get to a different operation, we're going to do different rules. All right, let's do some more examples to see this in practice, because we've seen about 80% of the picture for addition. Let's do another example here. And we're going to do this on this page here. I didn't capture anything. Hold on. All right, there's our example. I can't see it because Photoshop keeps putting a window in the way. There we go. So we're going to solve this just like we do the previous problem. I'm going to set up my problem in a different color. Hold on. I can't undo anymore, so I'm going to do it this way. Photoshop, you're weird. 4.83 minus 0.7. And so let's do our subtraction just like we would normally. 3 minus 0 is 3, 8 minus 7 is 1, 4 minus 0 is 4. Then the next move is to consider sig figs. I'm going to go from right to left, so I'm going to look in this position. Are there any question marks? Well, yeah, I don't know if 3 minus question mark is actually 3. So I cannot keep this number. So we don't get to keep that. How about right here? There are no question marks. All the digits are known or closely estimated. So I get to keep from the 10th position on over. So, wow, that's... What on earth? There's like a secret code hidden in here. That's really weird. I don't know what happened there. Wow, I'm using the eraser. It's like calling old stuff back. That's strange. Anyway. So the answer that I would report here would be 4.1. Okay. I don't get to keep the hundredths place because I didn't know what the hundredths place was with this other value. And if I subtract an unknown quantity, the result is unknown. But based on the information that I have, it's reliable that the tenths place is probably a 1, but it might be the next digit lower depending on what that question mark is. If that question mark's a big number, then it'll be 4.0 something. If it's a small number, it'll be 4.1 something. All right. So let's do another example here. Let's add these two numbers together. But before I do that, I'm going to try and erase everything again. Just in case, like... Let's see if it does that again. No, it's not, so that's good. Just in case, like, it didn't erase and I don't know. Photoshop doesn't like my graphics card or something. So same thing, we're going to set this up. I'm going to do the addition as normal. 9, I've sort of done this a little bit crooked here, but that's okay. All right. And then we're going to do the same sort of analysis here. And you can tell very quickly that these first three positions aren't going to help me any, so I'm not going to get to keep these. But then we get over here. And what I need to do now is look at this 0 and determine, is this 0 known or is it unknown? Is it actually a question mark and it just got rounded? Well, how many significant figures are in 7300? This 7 and this 3 are known, but these zeros are placeholders, which mean that they could be any number. And if they're any number, they're question marks, and so I don't get to keep this digit because this has a question mark. I don't get to keep this digit either. It has a question mark. So I have been moved all the way down to this position, the hundreds place, based on this value. And so I would report my answer as, huh? Would I report it as 74? No, this is the same situation as before with the, oh, I owe you $3,996. I'm going to round it to 4, right? So what we would do then is we would then put placeholder zeros in. And so this is the answer I would report for this problem. So 7,300 plus 139.228 would give you a result that when rounded to the hundreds place only gives you 7,400. We lose all the rest of the information because those are placeholder digits. They are not known. Now, as you can see, that's kind of a bizarre result. Here's the last result that we can get that's the most bizarre. Let's add these two numbers together. And then we'll explain why this is happening and why it seems counterintuitive. So if I'm going to add 3,000 plus 6, and let me make sure I line them up correctly this way. Let's count Sig Figs in each number just to prep ourselves. So that's these two. Now I'm going to do right to left here. Do I get to keep this number? No, because that's a placeholder. It's unknown. How about this number? No, it's a placeholder. Unknown. No, it's a placeholder. How about this one? Yes, this is fine. Now, if you're wondering, well, what about these? These aren't Sig Figs for 6 in front, but we know their value for sure. They are 0. So if you go past a number, these are known values, and the known value is 0. We just don't write those zeros because that's not how you write numbers. Otherwise, you'd have to write an infinite number of zeros ahead of it. So since this is the place that I'm rounding to, we round this number to this result. So in this class, 3,000 plus 6 is 3,000. And if you are looking at that and going, what the hell? I don't blame you. But let's take that result and let's try and draw a picture out of it. Yep, I broke your brain. I am not surprised. Let's try and draw a picture out of this, though. I'm going to put a picture. This is a bin full of marbles, and the bin only has crude measurements on it. Okay? And I have this many marbles inside. They're really big marbles because I don't want to draw this forever. Okay? There are tons of marbles inside this bin. If you had to estimate how many there were, how many marbles would you write down based on this scale? Type your answer in the chat. How many marbles are in my bin based on the number that I just, or based on the scale that I wrote? That K is 1,000, by the way. That seems totally reasonable. About 22,000, right? Okay. Now what I'm going to do is I'm going to, in the night, I'm going to throw my grappling hook rope down here, and I'm going to climb down here. This is me with my, like, ninja bandana or whatever. And I'm going to steal... Boop. I'm going to steal, like, 7 marbles, because that's really all I can carry. So I'm going to subtract 7 from this bin. How many marbles are now in the bin? Is it the number you just said, minus 7? Or is it the same number? It's, yeah, meh. Meh is the exactly right answer, right? It doesn't affect it. It's too small. Here's another example. Let's suppose that you win the lottery and get $657 million as a result. You're new to this millionaire thing, so you celebrate in the only way that you can. You go out and buy a Big Mac for $6.99. How much money do you have left? Is it $656,999,993? Or is it screw all those other numbers in like the thousands place? Who gives a shit about that anymore? I have $657 million, right? If you have this much money, there's a reason we write M after it. And that's because these numbers down here, we don't give a shit. You could give away $400,000. That's more than I will make in 5 or 6 years. You just give it away, and it doesn't even affect this number. Right? Because those zeros have been rounded. So when you do problems like this, where the magnitude is so different between sig figs, you get a really weird result. And that's because the tinier number cannot affect the bigger number. Okay? This happens all the time when you're doing these sorts of algebraic problems. But it makes sense because a big, poorly estimated number doesn't get affected by little tiny precise numbers. Let's suppose that I am 6'0". Yesterday I grew 0.008 inches because, I don't know, my hair got that much longer and it sticks straight up. Whatever, right? How tall am I? I'm still 6 foot, right? Because you don't give a shit about those tiny, tiny changes. That's not going to show up on a ruler. If you measure the population of Seattle, it's like 900,000. Yesterday, a family of 4 moved in. They're working at Amazon. How many people live in Seattle now? It's not 900,004. It's still 900,000. That estimate is very loose. And so that's why this is happening, and we have to account for that. And so Sig Figs in addition accounts for that, based on error that is present in these numbers. Okay? All right. So this number is not precise compared to this number. So I will get a bogus answer. Or at least it seems bogus, but it's actually correct. All right, so now let's go on to multiplication. Let's talk about error with this too. If I was trying to find the area of this rectangle, area is just length times width, right? So I would just multiply these numbers together. Now, there is error associated with my measurements if I only have a small number of sig figs multiplied by a large number of sig figs. Remember how when you used to do multiplication, you would multiply two numbers and you do the long multiplication. You put like an X here, or you'd put a 0 or whatever, and you just keep doing this. And you did it over and over and over again, and then you added everything together. It's the exact same principle behind multiplication that applies to addition. There's just more steps. If I multiply all these numbers by question marks, I will just get question marks. And then that's going to carry over, and that's going to propagate through my answer until I get to some point where I stop getting question marks, right? And then all the numbers after that will be okay. We're not going to do this example because it would take an entire piece of paper to show where all the question marks are. What I will show you is the result of it, okay? And it turns out the result is really easy to interpret. Here's how we deal with sig figs when you multiply or divide. You're going to count the number of sig figs in each value as written. Here's a value as written, and here's a value as written. How many sig figs does 14.2985 have? It has 6. Good. How many does 6.4 have? 2 sig figs. Good. Your answer will have the fewer number of sig figs when you do this problem. What's fewer, 6 or 2? Well, 2 is, right? So my answer will have 2 sig figs. So now I just punch this into the calculator, get whatever answer I should have, and just keep the first 2. So that's what we're going to do. So there's the correct number of sig figs. I'm going to multiply these numbers together, and I got that. Since 2 is the fewer number of sig figs, my answer will only have 2 sig figs. When I do this, I got to start from the left and go to the right. It would make no sense if I kept these as my numbers and said the answer was 4. Like, that's not right. So I got to start from the left and work right. I'm going to keep the first 2 digits here. I have a 5, so I'm going to round this up. So the answer I would report would be 92. Again, I'm doing standard rounding. I actually forget if bankers is round to even or round from even. I think it's round to even, but this would follow bankers. But I'm just doing standard rounding. I ignore bankers rounding. All right. Let's do some more of these. Oops. I thought I had a slide with more of these on there. Hold on. Multiplication and division is pretty straightforward, but I would still like to do more examples. Oh, no, I guess that's all the examples I have. Well, I can make up some examples. So I'm going to have you try some of these problems. So what I'll do is we'll clear everything first. And then what I'm going to do is I'm going to put some problems up here. So let's do 8.326 divided by 0.414538. So I want you to try and do this problem, and then we'll do another one. We'll do 7,300 times 0.28419. And then finally, I'm going to do 528.6386 divided by 3.3. All right. I want you to try and do those problems and give me the answers and report them in the chat when you've got them. Okay? We'll go over the answers together in just a second. All right. I see some answers in the chat, so let's go over the results together here. Where'd my stylus go? There it is. Okay. So the way that I do these, for multiplication and division, I just type stuff into the calculator. I can't show you my TA83 screen right here, but I assume you're all doing something very similar. So I'm just punching in all of the numbers for... I've already messed up. Hold on. 0.414. 538. And when I hit enter, I'm going to write down the number that the calculator spits out. 20.0850103. I do not need that many digits, though. How many should I keep? Well, this number up here has 4 sig figs, and this number down here has 1, 2, 3, 4, 5, 6. I have an eraser. What am I doing? 6 sig figs, which is smaller. 4 is smaller than 6, so I'm going to keep the first 4. So I would report 20.09 as my answer. If you report 20.08 because you're doing banker's rounding and you're rounding to even, that's fine. Generally speaking, on Canvas, when you punch in a number, I allow you to be off by 0.1 in the last digit. If you're off by more than that, then you've made a mistake. All right, number 2, 7,300 times 0.28419. My calculator says 2,074.587. That's too many digits. Let's see if we could fix that. This is 2 Sig Figs, because remember, these are placeholders. These are actually Sig Figs. This is 5 Sig Figs. What's smaller? 2 is smaller than 5, so I only keep the first 2 digits. But I can't report 21 as the answer, because 73,000 times something is not 21. So I need, there's my decimal point, I need at least 2 zeros to go there. So that's the answer I'd report. And then finally, this one down here, 528.6386 divided by 3.3. When I do this, I get 160.1935152. I mean, we already know this is going to restrict our answer. There you go. All right. Very important. Use these rules for multiplication and division only. Okay? So, when I say these rules, what I mean is the number of Sig Figs. Right? It is super easy to apply, oh, I have a number with 6 and a number with 3 Sig Figs and a number with 2 Sig Figs. I'm going to have 2 with my answer. And it's the second you do addition, that falls apart. Don't do that, okay? If you're only doing multiplication or division, then yeah, you just punch it all in your calculator and then check for Sig Figs, just like we've been doing. The issue we're going to run into is when we start combining operations, and that's what we're actually going to do on the next problem. Here's a common type of problem that you see in this class. This is the sort of problem that you would do if you were doing an error analysis. You subtract or add 2 numbers and then divide by, say, an average of something else. So you're doing addition and subtraction alongside multiplication and division. Or maybe you're solving an algebraic expression like this. And we'll just say that this equals y. What would the first step be? Well, it'd be subtraction. Then the next step would be division, right? So we have to do both types of operations all the time. How do we do this? And the answer is, here's the short version. Every time you change operations, you stop and consider Sig Figs, okay? So you have to be careful. So what's the first thing we would do with this problem? Well, I have a subtraction in parentheses on top of a division. We're going to do PEMDAS, right? Please excuse my dumbass sibling. That's what PEMDAS means, right? Parentheses, exponents, multiplication, division, addition, subtraction. So please excuse my dumbass sibling. That's what that means, right? That's what I used growing up, because my sibling was a total dumbass. But anyway. Something about Aunt Sandy or whatever. All right. These two are prioritized together, and these two are prioritized together as well, just in case you forgot your algebra rules. Since we have something in parentheses up here, we're going to do that first. So I'm going to punch this into my calculator. 73.8 minus 70.983. And when I do that, this is the result that I get on top. How do I know where to round it? Well, I would have to have set it up vertically. Shouldn't I have done that? Well, when you get really proficient at this, you don't actually have to do this step anymore. This is just what my calculator spit out for me. But I'm going to show you how you can get to this and get to the correct answer, which should just be this, and chop these off in a second. When we do the analysis here, you could say, okay, no, no, yes. And say, okay, that must be 2.8. The other way you can do that is you can say, okay, I have a tenths place, and there's my tenths place. I have numbers that are further than that, so I'm going to do the subtraction and round to the tenths place, because, again, addition and subtraction care about places, which is why we're doing it this way. Okay. So once I've done that, I then go to the next step. I've done my subtraction. There's my result. Now, you can keep the other digits in the calculator if you'd like to, but how error works is that it's going to get rounded away anyway and affect that digit. We're going to be off by 1 in the last digit regardless. So keeping extra numbers and then just remembering that you have 2 sig figs is fine. It does add an extra step, though. You will get an answer that is technically more correct by doing that. Because that'd be the... If I were to just enter 2.8 into the calculator, it would be like doing this for my result. So I'm just erasing this to make this more clear. So for example, if I had... It would be like if I round my answer and used this rounded result, it would be like me saying, well, these numbers don't matter, so I'm just not going to include them anyway. And so we'll just go 18 minus 9 is 9. And then use that. Notice that this number is slightly different than what I got because these numbers do affect it, right? So keeping your extra digits in the calculator, but then noting that you only get to have this many sig figs from that result is okay. Okay. So in other words, the point of doing this calculation wasn't necessarily to get 2.8. It was to get this information here, 2 sig figs. Now when I do this, I'll just do 2.8, whatever is in the calculator, which I have 2.817, divided by 2.639. But when I hit enter, whatever result I get, I only get to keep 2 sig figs out of that. And so my calculation is 1.0674, which I'm going to then round to 1.1. Okay. In this circumstance, if I had kept 2.8 and just used only that and then divided by 2.639, I think I would get the same result. It would still round to 1.1. In some cases, it won't. And thus, keeping those extra digits from previous operations is important. So make sure that you're keeping the numbers along with you, but noting at each step how many sig figs your result gave you. Because those sig figs will affect your eventual answer. Okay. Notice that of all of the numbers that we started with, no number up here had 2 sig figs, but our answer did. And that's because we had a combined problem. So be careful when doing combined problems. Don't just apply the multiplication division rules. You'll get it wrong. So to keep the number in the calculator, you only keep 2 sig figs. Yes, that's right. Because when I did this subtraction right here, 73.8 minus 70.983, I shouldn't keep erasing this. When I do this subtraction here, I don't know if that's right even. I gotta do that again. There we go. That's what I meant to write. When I do this subtraction here, I don't get to keep this because this is a question mark. I don't get to keep that one. I get to keep this value as my answer, so I should have 2 sig figs for my result. But I'm going to put the whole number into the calculator anyway. And note that I have 2 sig figs, which is why I wrote it as 2 sig figs. Now, that said, if you did only keep 2.8, you would get an answer that's really close anyway. But the more steps there are, the more error you will introduce. And we want to keep the effects of known numbers as long as we can. All right. This last little example is just a, hey, this is a rounding primer. What should I do to round numbers? Well, if you have X number of sig figs and you're only allowed to keep so many, again, remember you work from left to right. So if I wanted to round this to 3 sig figs, this number would become 30.4. And then there's just a small rounding primer down here. This is, again, standard rounding. I don't care about bankers rounding. If we were doing 75 data points, then yeah, I would care about it. It'd be more statistically significant. But for regular rounding, just round towards the nearest 0. Where 5, you just round up. Finally, your calculator doesn't know what sig figs are, and it will delete zeros. So if you do this operation in your calculator, what you end up getting for a result is you just get 8. But if I were to put this in the not the calculator, I'm sorry. If I were to do this vertically, this is the result that I would get. So 2 and 8 is 10, 6 plus 3 plus 1 is 10, 6 plus 3 plus 1 is 10, 6 plus 1 plus 1 is 8. And so this is the correct answer because I know all of my digits to the thousands place in both. So I get to keep all those zeros. So my answer for this addition problem would have 4 sig figs. But your calculator would punch this in and it'd go, hey boss, I got 8. Did I do good? And you'd be like, no, calculator, you did bad. Because your calculator doesn't know what sig figs are. So be careful if you are punching numbers into the calculator, because it will just print out whatever number it has space for, and it'll omit all other zeros. If you get a situation like that where your answer needs to be, like, I don't know, say 5 sig figs, and this is what your calculator says, you have to put in the other zeros yourself. Okay? Just be mindful of that. You may have to enter extra zeros to have the correct number of sig figs. This comes up often on labs where I have you add or subtract 2 numbers, and the last digit just ends up being 0. You do have to include it. It is a known number. All right. If you ever use exact numbers, remember that exact numbers have infinite sig figs. So that means that if you're adding something to an infinite sig fig number, it's never going to affect it. So the other numbers will influence it. So if you have operands left to do, don't round. Keep all of your numbers for as long as you can in the calculator, but note at each step how many sig figs your result should have. So like if you have a number that you add to another number, and then you multiply, and then you add to another number, don't round until the very end if you can help it. Now, that's not always practical, because if I asked you to do a problem and you report the answer to the correct number of sig figs, you might just write that down and then pass that to somebody else, and then they would use that number in another operation, and it's okay. By keeping the numbers, you preserve as much information as you can, and the uncertainty gets wrapped up in the last place anyway. It's this digit, right? If you did keep that or you didn't keep that information, and you, like, say you just rounded it every step and then went to the next thing, you would slowly accrue a different answer than what you would do if you had kept all the digits every time. But you will not get to the point where there is so much deviation that it would change the number appreciably. Okay? At least as far as significant figures are concerned. That's why sig figs are how they are. These are all the numbers we know for sure, or at least are reliable. They're within plus or minus 1 or 2 of the last digit. And that error on the last digit comes from these types of rounding and rounding errors, basically. All right. I'm going to give you a bunch of practice problems to do. I want you to try to do these. Report your answer to the correct number of significant figures, and we'll go over the answers together in about 5 minutes. Type your answer in the chat when you are finished. When you have your answers, make sure you type them in the chat. That's just to let me know that some people are finished. And then we'll go over them together. All right, let me resize this to get a few of these on the screen at once. There we go. So clear. All right, I gotta move this thing. I have this button that like hovers over everything, and I don't want it there. Can I put it here? Yeah, that's fine. Okay. It's part of Photoshop, and when it's on the screen, it's in the way. All right, so I have 0.019 times 21.39. So this is problem number 1. It's multiplication, so I'm going to punch it in the calculator. And the result that I get is 0.040641. How many sig figs should my result have? Well, the first number has 2 sig figs, and the last one has 4, so this one should have 2 sig figs. Which means these are placeholders, they don't count. These are the first 2 I should keep. And there's my answer, 0.041. All right, number 2. 8.341 divided, or I'm sorry, 8.321 divided by 4.1. When I punch it in the calculator, I get 2.029512195. That's way too many digits. How many sig figs should I keep for that one? Top number is 4 sig figs, the bottom number is 2, so I would only keep 2. That's the answer I would report. For number 3, I'm going to set it up vertically to solve it. So 3,000, 20.3, and then 0.009. There's my addition, but when I start going left to right here, I got question marks in here. These are question marks. These are question marks. These are even placeholders. So I can't use any of these digits until I get to here. So I would round to this position, and my answer I would report would be 3,000. Now, keep in mind 3,000 without the dot. Don't put the decimal point, or else it'll get marked wrong. For the other one, 4.33 minus 3.62. Let's do the subtraction. 3 minus 2 is 1. 13 minus 6 is 7. And then 3 minus 3 is 0. I round to this position. Everything is known, so this is the answer I'd report, 0.71. Now, keep in mind, I had 3 sig figs up here and 3 sig figs here, but my answer only has 2. Addition and subtraction does not care, so don't add in extra zeros because you don't know those numbers over here. If I put a 0 in this spot right here, that would mean that I knew something about these numbers, but I don't know that, so you can't add include those. Number 5 and number 6. These are just checks to make sure that you know the rules. So for this first one, I have 6.000. I'm actually going to write this one out. Times 2.000. When I multiply that in the calculator, it just says 12. That's it. That's all the calculator says. How many sig figs should I have? Well, this has 4 sig figs. And this is 4 sig figs. So my answer should also have 4 sig figs. And so we'll do that. There you go. If you add that extra 0 in there, right here, then you have 5 sig figs, and that would be incorrect because you're not doing addition, you're doing multiplication. Now you might be looking at that and saying, well, wait a second, 6 times 2, isn't that the same as just doing 6 plus itself? And the answer is, yes, but this is not 2, this is 2.000. You would need to do exactly 2 in order to do that and keep the sig figs. So as written, I am multiplying 6 to 4 sig figs times 2 to 4 sig figs, and not 6 to 4 sig figs times exactly 2. Okay, so keep that distinction in mind. Make sure you're following the rules. The next one is a combined operation. I'm going to do the parentheses first. 4.281, 37.3. We're going to do our addition here. 18504. Oops, that's wrong. Hold on. This is a 1. All right, now that I know that, we got to round to sig figs. Oh, can't do this. I got a question mark. Can't do this either. This is going to be the first spot that I round to. So my answer that I should report would be 41.6, which has 3 sig figs. But we're going to take that answer and we're going to throw it into the calculation times 0.00390. And when I do that on the calculator, the calculator spits out 0.1621659. I had 3 sig figs for my first number and 3 sig figs for this number, so my answer should also have 3 sig figs. And there you go. So I would report that as the answer to that problem. And then finally, this last one down here, same thing. We'll do the division first, since it's in the parentheses. And when I punch that into the calculator, 52.500 over 3.6, I get 14.583333333333. This has 5 sig figs. This has 2 sig figs, so my answer should only have 2 sig figs. So if this was the problem that I was doing, I would have reported 15 as my answer. But since we're doing something else with it, we'll just carry it over here as is and do the last part, which is subtracting 11, knowing that these are the only numbers that are significant. So these are really all question marks. But so are these down here anyway. So when I do the subtraction, I would get this, which when I round to this position, because I'm doing subtraction, the answer I report would be 4. Remember, these are all unknown. I don't get to keep any of those numbers, but I do get to round, so that's where I'm reporting my answer. All right. That's how you do these. And I see a lot of wrong answers. Not because you're bad at math or something, but because this is new. So what I want you to do, because that's the end of chapter 2, we're gonna do scientific notation on Thursday's lecture, and then the quiz will appear. I'm actually gonna post the quiz tonight because scientific notation is very short, and so you can get started on that. But I really recommend that you do the exercises for this chapter, as well as the worksheet, because Unit 2, this is what we're going to be doing for the rest of the quarter, and you need to make sure that you understand how these rules apply and when to correctly apply them, okay? So that you'll get the right answer every time. Are there any questions that you have for me? Let me know in the last few minutes here, because that's all we're going to do. If you have other questions that you want to ask me later, keep in mind that the class Discord is going. I posted a new link to that. That is available now. As well, you can always email me. Just let me know if you have any questions about this, because this is challenging for what it is. This is a whole new way of doing math, and I understand it takes time. I want to thank everybody for coming to lecture today. We will continue tomorrow with the first lab lecture. So please attend for that on Wednesday to get an idea of what it is we're going to be doing in the lab periods and how the lab assignments work. Thanks for coming, and I will see you tomorrow. Have a wonderful evening, and take care.